Hello, in this lecture we will answer on two questions. In the first question, we will find out the area of this trapezoid ABCD that blocks this circle. And in the second question, we will find out the area of this green shape that is inside rectangle ABCD. So we start with the first question. So in the drawing we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length, and this is side DC that is equals to x over to 7 over x units in its length. In addition, this is angle BAD, that is a right angle, and this is angle CDA, that is also a right angle. I repeat again, our mission is to find out the area of this trapezoid ABCD. So first of all, what is trapezoid? Trapezoid is a quadrilateral with one pair of parallel sides. Again, trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AB is parallel to the opposite side DC. And therefore, this quadrilateral ABCD is defined as a trapezoid. The two parallel sides, that is to say AB and DC, they are defined as the bases of trapezoid ABCD. So AB is the base and DC is the second base. And the area of a trapezoid, the area of this trapezoid ABCD equals to the sum of its two bases. Side AB equals to B, side DC equals to A, and the two bases are the two parallel sides, that is to say AB and DC. So the sum of the two bases is B plus A or A plus B times the height, that is h, over 2. And again, the area of this trapezoid ABCD equals to the sum of its two bases, that is A plus B times the height, that is h, over 2. A plus B times h over 2. The height h must create 90 degrees with the two bases. The height h creates 90 degrees with base DC. This angle equals to 90 degrees, and this angle also equals to 90 degrees. And it creates 90 degrees with the base AB, because this angle equals to 90 degrees. So in conclusion, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of the trapezoid equals to the sum of its two bases. In this case, it is A plus B times the height, that is h, over 2. The height must create 90 degrees with the two bases. Okay, so first of all, we will define the points of tendencies of trapezoid ABCD with this circle. We will define the point of tendency of tangent AB with this circle, this point, as E. Likewise, we define the point of tendency of tangent AD with this circle, this point, as F. we define the point of tendency of tangent BC with this second this point as G, and finally we define the point of tendency of tangent DC with this second this point as H. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from common standpoint to a circle are equal. So in the drawing we have a circle, and this is the common standpoint point P. From this common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule 2, PA equals to PB. You can actually implement rule 2 in our drawing. Well, because if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this circle, tangent AE and tangent AF, and according to rule 2, they are equal to each other. So if we define the length of this tangent AE as Y, then the length of this tangent AF must be also equal to Y, according to rule 2. Likewise, we focus on this common standpoint point B. From this common standpoint point B, we have two tangents to this circle, tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of this tangent BE as Z, then the length of this tangent BG must be also equal to Z according to rule 2. Next step, we focus on this common standpoint point C. From this common standpoint point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, we focus on this common standpoint point D. From this common standpoint point D, we have two tangents to this circle, tangent DF and tangent DH. And according to rule 2, they are equal to each other. That is to say, DF equals to DH. So if we define the length of this tangent DF as T, then the length of this tangent DH must be also equal to T according to rule 2. So, what is the value of AB plus DC? Again, what is the value of AB plus DC? From the drawing, it is very easy to see that AB according to rule 2 equals to Y plus Z, and DC equals to T plus N. Oh. So in total, AB plus DC equals to Y plus Z plus t plus m. This is from one side, but from the other side, what is the length of side AD with side, what is the length of side AD plus side BC? AD plus BC. AD equals to y plus t plus BC. BC equals to z plus m. Okay, in total we found out that AD plus BC equals to y plus t plus z plus m. Here we can change the order of the letters according to the algebraic identity that a plus b equals to b plus a. So y plus t plus z plus m equals to y plus z plus t plus m. Just change the orders of the letters of this expression. And finally we actually found out that AD plus BC equals to y plus z plus t plus m, and AB plus DC also equals to y plus z plus t plus m. So those two expressions, the green color, they are both equal to the same third expression, that is y plus z plus t plus m, therefore they are equal to each other. That is to say, AB plus DC equals to AD plus equals to AB plus DC equals to AD plus BC. We will define the length of this side AD as A AD equals to A according to our definition. We define the length of this side BC of trapezoid ABCD as B. So BC equals to B according to our definition. So according to equation 1, AB plus DC equals to AD plus BC. So AB equals to x according to what is given as the question. So we solve AB by x plus DC. DC equals to 7 over x according to what is given as the question. So we substitute DC by 7 over x, and on the other side of the equation 1 we have equals to AD plus BC. AD according to our definition equals to A. Again, AD equals to A, so we substitute AD by A plus BC. BC equals to B according to our definition, therefore we will substitute BC by B. So in conclusion, we should found out that according to equation 1, x plus 7 over x equals to A plus B. And again, according to equation 1, we should found out that x plus 7 over x equals to A plus B. In the next step, we'll do a construction That is to say, from this point B, we will draw perpendicular on DC. Again, from point B, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B inside DC, this point is point S. By doing this construction, we created here quadrilateral ABSD. This is quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because of the simple fact that 270 degrees, that is the sum of these four angles, plus 90 degrees, is 360 degrees, that is the sum of the angles in any quadrilateral. So inside quadrilateral ABSD, we have 4 right angles. According to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Therefore, we will relate to this quadrilateral ABSD as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB equals to the opposite side DS. But AB is x, according to what is given us in the question. Therefore, DS, the opposite side DS, must be also equal to x. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A according to our definition, therefore BS must be also equal to A. So by doing this construction, we actually created here the right triangle BSC. What is the length of this side SC of triangle BSC? From the drawing it is very easy to see that SC in total SC equals to DC minus DS. So write it down. Again, SC equals to DC minus DS. SC equals to DC minus DS. So SC equals to DC. DC is 7 over x according to what is given us the question, minus DS. We just found out that DS equals to x. So in total, SC equals to 7 over x minus x. So in the next step, I'll copy this green right triangle BSC in a new page, and we will implement the Pythagoras theorem on this green right triangle BSC. So here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. side BS equals to A, the hypotenuse BC equals to B according to our definition, and we just right now found that the side AC of the green triangle equals to 7 over x minus x. So actually, this is the right triangle BSC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BSC, BC square equals to BS square plus SC square. The hypotenuse BC equals to B according to our definition, therefore BC square is B square, and it is equals to BS square. BS is A, also according to our definition, therefore BS square is A square plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. So according to equation 1, we found out that B square, this is actually equation 2. According to equation 2, we found out that B square equals to A square plus 7 over x minus x square. While according to equation 1, we already found out that x plus 7 over x equals to A plus B. So according to equation 1, we know what is the value of x plus 7 over x, but in the equation 2 we have the value of 7 over x minus x. So how we can substitute 7 over x minus x by 7 over x plus x? We use the algebraic identity that states that A minus B square equals to A square, A plus B square, and then A minus B square equals to A plus B square, minus 4 times A times B. If you open the brackets on both sides of this equation, you will definitely find out that the left side of this equation equals to the right side. So A minus B square equals to A plus B square minus 4 times AB. If we define x as A and B as 7 over x, we get that if we define, actually here we have 7 over x minus x. So if we define A as 7 over x and B as x, we find out here that 7 over x minus x squared according to this algebraic identity will be equal to 7 over x plus x squared minus 4 times A is 7 over x times B, that is x. So in total we actually found out that 7 over x minus x squared according to this algebraic identity equals to 7 over x plus x squared minus 4 times 7 over x times x. So here we have x in the numerator and x in the denominator, so x will get cancelled. So if we found out that according to this algebraic identity, 7 over x minus x squared equals to 7 over x plus x squared minus 4 times 7, that is minus 28. So in total, according to equation 2, we actually found out that b squared equals to a squared, and we have here 7 minus x squared according to this algebraic identity equals to 7 over x plus x squared minus 28. So according to equation 2, we actually found out that b squared equals to a squared is actually plus 7 over x plus x squared minus 28. But according to equation 1, x plus 7 over x equals to a plus b. So if x plus 7 over x equals to a plus b, it means that x plus 7 over x squared will be equal to a plus b squared. So we substitute 7 over x plus x squared by a plus b squared according to this equation, equation 1. And we have to subtract minus 28. And we have to add also here a squared according to this equation, equation 2. And it is equals to b squared according to this equation, equation 2. In conclusion, we actually found out that b squared, according to equation 2, b squared equals to a squared plus a plus b squared minus 28. Here we'll open the brackets on this side of this equation, equation 2. And finally we get that according to equation 2, in this side of equation 2 we have b squared that is equals to a squared plus a plus b squared. A plus b squared equals to a squared plus b squared plus 2 times a times b minus 28. So actually, according to equation 2, we found out that b squared equals to a squared plus b squared plus 2 times ab minus 28. Here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared, in this side of the equation we left with nothing, that is to say 0. And 0 equals to a squared plus a squared is 2a squared plus 2ab minus 28 equals to 0. This is according to equation 2. Here we add 28 to this equation, equation 2, and we get that according to this equation, equation 2, 0 plus 28 is 28. This equals to, on the other side of the equation we have 2a squared plus 2ab. So according to equation 2, we found out that 28 equals to 2a squared plus 2ab. Here we divide this equation, equation 2 by 2. And finally we get that according to equation 2, 28 over 2 is 14 equals to 2a squared over 2 is a squared plus 2ab over 2 is ab. So in conclusion, according to equation 2, we found out that 14 equals to a squared plus ab. Well, according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So, what is the area of trapezoid ABCD? According to the formula that I presented to you at the beginning of the lecture, the area of this trapezoid ABCD equals to the sum of its two bases times the height over 2. So what are the two bases of this trapezoid ABCD? Actually, the two bases are AB and DC. Why the two bases are AB and DC? Because of the fact that ABSD is a rectangle, and you know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC, and it's parallel to AB. So if part of the straight line DC is parallel to AB, it means that the straight line DC itself must be also parallel to AB. If we found out that DC is parallel to AB, and therefore the two parallel sides in trapezoid ABCD are DC and AB. So the bases of trapezoid ABCD are AB and DC. And therefore the sum of the two bases is AB plus DC. So it is the sum of the two bases that is equals to AB plus DC times the height over 2. The height is AD. Why the height is AD? Because of the fact the height AD creates 90 degrees with the two bases. Here the height AD creates 90 degrees. This angle equals to 90 degrees. It creates 90 degrees with the base AB. And the height AD also creates 90 degrees with the base DC. This angle equals to 90 degrees. And therefore the height is AD. So this times the height AD over 2. So the area of trapezoid ABCD equals to AB is X, according to what is given as the question, plus DC. DC is 7 over X, according to what is given as the question, times the height AD. AD is A, according to our definition, divided by 2. So we found out that the area of trapezoid ABCD equals to X plus 7 over X times A over 2. But according to equation 1, X plus 7 over X equals to A plus B. Therefore, we can substitute here X plus 7 over X by A plus B. We do it now. So X plus 7 over X is A plus B. Therefore, in total, this expression equals to A plus B times A divided by 2. Here we will open the brackets of this expression, and we get that A times A is A squared plus B times A is AB divided by 2. So the area of trapezoid ABCD equals to A squared plus AB over 2. But we have already found out that according to equation 2, A squared plus AB equals to 14. Again, A squared plus AB equals to 14, therefore we can substitute A squared plus AB in this expression by 14. So we do it now. So A squared plus AB is 14. So in total, this expression equals to 14 over 2. 14 over 2 is 7. In conclusion, we found out that the area of trapezoid ABCD is equals to 7 square units. And that is the answer to the first question. I repeat again. The area of this trapezoid ABCD equals to 7 square units. Okay, so in the next step, I present to you the second question. So in the drawing, we have rectangle ABCD. It is given as the question that side CB of this rectangle ABCD equals to 7 units in its length. Inside this rectangle ABCD, we have here line segment CP that is equal to 4 units in its length. This is line segment PQ that is equals to 2 units in its length. And finally, this is line segment QA that is equals to 5 units in its length. In addition, this is angle CPQ that is a right angle, and this is angle PQA that is also a right angle. I repeat again that our mission is to find out the area of this green shape. Okay? So first of all, we will join point C and A together by straight line. And we will define the intersection point of diagonal AC with line segment PQ, this point SM. Those two angles are defined as vertex angles, and know that vertex angles are equal to each other. So if we define this angle CMP as theta, then the other vertex angles must be also equal to theta because of the fact that they are equal to each other according to the rule that vertex angles are equal to each other. In the next step, we'll focus on this right triangle AMQ. In this right triangle AMQ, this angle equals to theta. This angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on this right small triangle PCM. On this right triangle PCM, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus theta. It is given us in the question that PQ equals to 2. Yeah, PQ equals to 2 units in itself. So if we define line segment PM as X, then line segment MQ must be equal to PQ minus PQ minus PM. Again, MQ equals to PQ minus PM. PQ is 2, PM is X, therefore in total MQ equals to 2 minus X. In the next step, we'll prove that those two right angles are similar to each other. That is to say, we prove that this right triangle MQA is similar to this right small green triangle CPM. So I write it down. We'll prove that this right white triangle AMQ is similar to this right small green triangle CPM. So, why those two right triangles are similar to each other? First of all, those are two vertex angles and they are equal to each other. Each angle equals to theta, therefore they are equal to each other. So this is angle PMC. In the right triangle PMC, and it is equal to this angle AMQ, in the right triangle AMQ. Repeat again, angle PMC in the right triangle PMC equals to angle AMQ in the right triangle AMQ. They are both equal to theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle CPM in the right triangle PMC, and it is equal to this angle, that is actually angle AQM in the right triangle AMQ. Repeat again, angle CPM in the right triangle PMC equals to angle AQM in the right triangle AMQ. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle PCM in the right triangle PMC, and it is equal to this angle, that is actually angle QAM in the right triangle AMQ. Repeat again, angle PCM in the right triangle PMC equals to angle QAM in the right triangle AMQ. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So in conclusion, we found out that all the three angles of this right triangle AMQ are correspondingly equal to all the three angles in this right green small triangle PQC, and therefore PMC, the right small triangle PMC, and therefore those two right triangles are similar to each other to each other according to angle similarity rule. So I write it down. The right triangle PMC is similar. This is the sign of similar to the right triangle AMQ according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PM in the right triangle PMC over side MQ in the right triangle MQA equals to side PC in the right triangle PMC over side AQ in the right triangle AQN. It again, we will derive that PM over MQ equals to PC over AQ. PM equals to X over MQ. MQ equals to 2 minus X, and it is equals to PC. PC is 4 over AQ. AQ is 5. So if we found out that X over 2 minus X equals to 4 over 5. Here we will cross multiply this equation and we get that 5x equals to 4 times 2 minus x. So here we'll open the brackets on this side of this equation and we get that 5x equals to 4 times 2 is 8 minus 4x. Okay, so here we add 4x to this equation and we get that 5x plus 4x is 9x equals to 8. 9x equals to 8. Here we will divide this equation by 9 and finally we get that x equals to 8 over 9. So actually 9:07 p.m. that is equal to x equals to 8 over 9. And MQ equals to 2 minus x. That is to say, MQ equals to 2 minus x. X is 8 over 9. 2 minus 8 over 9. 2 minus 8 over 9 is 1. And 1 and 1/9. So it is actually 9 over 9 plus 1/9 is actually 10 over 9. Again, 1/9 is 10 over 9. Okay. In the next step, I will copy the line AQPC in a new page and analyze this line AQPC. line segment AQ equals to 5 units, according to what is given in the question. This angle equals to 90 degrees. PQ equals to 2 units in its length. Line segment PC equals to 4 units in its length. This is angle CPQ, that is a right angle. So this is line AQP C to the cover from the original drawing. Here we will extend the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line. So this is one straight line. If we focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to the rule 3, that the sum of the angles on one side of a straight line equals to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle that equals to 90 degrees, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees, according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction. That is to say, from point C, we will do perpendicular on the extended AQ. Again, from point C, we will do perpendicular on the extended AQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and this extended AQ as N. By doing this construction, we created quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because the sum of three angles, that is 270 degrees plus 90 degrees, is 360 degrees. That is the sum of the angles in any quadrilateral. So inside this quadrilateral PC and Q, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral PC and Q as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. This is to say, in rectangle PC and Q, side PQ equals to the opposite side CN. But PQ equals to 2, therefore CN must be also equal to 2. Likewise, according to the same rule, in the same rectangle PC and Q, side PC must be equal to the opposite side QN. But PC is 4, therefore QN must be also equal to 4. In the next step, we'll join points A and C together by a straight line. By joining points A and C, we actually created the right triangle ACN. In the next step, we will implement the Pythagoras theorem on this right triangle ACN. According to the Pythagoras theorem, in the right triangle ACN, here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ACN, AC square equals to cn square plus an square. So we have already, so here ac square, that is the square of the hypotenuse, equals to cn square. Cn is 2, therefore cn square is 2 squared, that is 4, plus an square. An in total equals to 5 plus 4. Again, an in total equals to 5 plus 4, that is 9. So an is 9, therefore an square is 9 squared, that is 81. So in total we actually found out that ac square equals to 4 plus 81, that is 85. So ac square equals to 85. We know that according to what is given as the question, ABCD is a rectangle. And we also know that all the angles in any rectangle are right angles. All the 4 angles in any rectangle are right angles. And therefore, this angle ABC is equals to 90 degrees in its size. It is 1 out 4 angles of this rectangle ABCD. Therefore, it must be equal to 90 degrees in its size. In the next step, I will copy the big right triangle ABC in a new page, and we will implement the Pythagoras theorem on this right triangle ABC. Here by PT is the abbreviation for Pythagoras theorem. AC square, that is the square of the hypotenuse of the right triangle ABC. AC square equals to 85. Side CB of the right triangle ABC equals to 7 units in its length, according to what is given as the question. Carefully, this is the right triangle ABC that I got from the original drawing. In this right triangle ABC, AC square equals to AB square plus BC square. We have already found out that AC square equals to 85, so we solved AC square by 85, and it equals to AB square. AB is the missing side, so we will leave it as it is. AB square plus BC square. BC is 7, therefore BC square is 7 squared, that is 49. Here we subtract 49 from this equation, and finally we get that AB square equals to 85 minus 49. 85 minus 49 is 36, so AB square equals to 36. We take a root from this equation, and we get that AB equals to the square root of 36, that is 6. So we found out that this is side AB, that equals to 6 units in its length. So, what is the area of the green shape? The area of the green shape equals to the area of the big right triangle ABC But because of the fact that the area of the big right triangle ABC consists of this white triangle, we have to subtract from the area of this right triangle ABC the area of the white triangle, triangle AQM, because our mission is to find out the area of the green shape. So we subtract from the area of the right triangle ABC the area of this white triangle, triangle AQM. But the area of the green shape also includes the small right triangle CPM, and the small right triangle CPM is not included in the area of the right triangle ABC. Therefore, we have to add to the area of the green shape the area of the small green right triangle, triangle PCM. So in total, we should find out that the area of this green shape equals to the area of the big triangle ABC minus the area of this white right triangle AQM plus the area of this small green right triangle PCM. I repeat again, the area of the green shape in total equals to the area of the right big triangle, triangle ABC, minus the area of the white triangle AQM, plus the area of the small right green triangle, triangle PCM. The area of the right big triangle ABC equals to the base of the triangle, that is AB, times the height to the base, that is BC, over 2. Repeat again, the area of triangle ABC equals to the base AB times the height to the base, that is BC. Again, the area of the right green triangle ABC equals to the base AB times the height, that is BC, over 2. We have to subtract from the area of the right big triangle ABC the area of this white triangle, triangle AQM. The area of this right triangle AQM equals to the base of the triangle, that is AQ, times the height to the base, that is QM, over 2. Repeat again, the area of the right white triangle AQM equals to the base AQ times the height to the base, that is QM, minus 2, plus the area of this small green right triangle, triangle PMC. The area of this small green right triangle PMC is equals to the base, that is PC, times the height to the base, that is PM, over 2. Okay, I repeat again, the area of the green small right triangle PCM equals to the base, that is PC, times the height to the base, that is PM, over 2. So actually found out that the area of the green shape in total equals to the area of triangle ABC, is actually equals to AB 6 times BC 7 over 2. So in total, the area of the right triangle ABC equals to 6 times 7 over 2 minus the area of triangle, the white triangle AQM. This equals to AQ. AQ is 5 times QM. QM is 10 over 9, all divided by 2. So in conclusion, we found out that the area of the white right triangle AQM equals to 5 times 10 over 2 times 9, plus the area of the right green small triangle PCM, that is equals to PC. PC is 4 times PM. PM is 8 over 9 divided by 2. So in total, we found out that the area of the green small right angle PCM equals to 4 times 8 over 2. So the area of the green shape in total equals to 6 times 7 is 42, and 42 over 2 is 21. So the area of the green, the area of the right big triangle ABC is 21 square units, minus the area of the right triangle AQM. The area of the right triangle AQM equals to, here we have 10 over 2 is 5, 5 times 5 is 25, so in total this expression equals to minus 25 over 9, plus the area of the green small right triangle PCM. This expression equals to 8 over 2 is 4, and 4 times 4 is 16, so in total this expression equals to 16 over 9. So in total the area of the green shape equals to 21, and we have here minus 25 plus 16 over 9. So the area of the green shape equals in total to 21, and here we have minus 25 plus 16 is minus 9. So in total this expression equals to minus 9 over 9. So the area of the green shape in total equals to 21, and minus 9 over 9 is minus 1. 21 minus 1 is 20. So in conclusion, we found out that the area of the green shape equals to 20 square units. And that is the answer to the question. Repeat again. The area of the green shape, the area of this green shape equals to 20 square units. So in the next step, I will summarize the lecture. We start with the first method, of course. We start with the first question. In the first question, our mission is to find out the area of this trapezoid ABCD. So, in the drawing we have trapezoid ABCD. We know that side AB equals to x, side DC equals to 7 over x. This is angle BAD, that is a right angle, and this is also angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? Trapezoid is a quadrilateral with one pair of parallel sides. Again, trapezoid is a quadrilateral with one pair of parallel sides. In the drawing we have trapezoid ABCD. This trapezoid ABCD, side AB is parallel to side DC, and for that reason quadrilateral ABCD is a trapezoid, because side AB is parallel to side DC. Those two parallel sides, that is to say AB and DC, are defined as the bases of this trapezoid. That is to say side AB is the one base, and the second base is side DC. According to our definition, AB equals to B, DC equals to A. So the area of trapezoid ABCD equals to the sum of its two bases, that is to say B plus A, times the height, that is h, over 2. The height h must create 90 degrees with the two bases. You can see here that h creates 90 degrees with the base AB, and it also creates 90 degrees with the base DC. Repeat again, that the area of this trapezoid ABCD equals to A plus B, that is the sum of the two bases, times the height, that is h over 2. So the area of trapezoid ABCD equals to A plus B times h over 2. Okay. So in the first step, we actually defined the point of tendencies of this trapezoid ABCD with this circle with letters. That is to say, we defined the point of tendency of tangent AB with this circle, this point as C. Likewise, we define the point of tendency of tangent AD with this circle, this point as F. We define the point of tendency of tangent BC with this circle, this point as G. And finally, we define the point of tangency of tangent DC with this circle, this point as H. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of this tangent AE as y, then AF must be also equal to y, according to rule 2, because they are equal to each other. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BE and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BE equals to BQ. So if we define the length of tangent BE as Z, then tangent BG must be also equal to Z, according to rule 2, because they are equal to each other. Likewise, we focus on this common external point, point C. From this common external point, point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then CH must be also equal to M according to rule 2. And finally, if we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle, tangent DH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DF equals to DH. So if we define the length of tangent DF as T, then the length of tangent DH must be also equal to T, according to rule 2, because they are equal to each other. Okay. In the next step, we define side AD as A and side BC as B. So, what is the value of AB plus DC? AB plus DC. So, AB equals to Y plus Z, DC equals to T plus M. So, in total, AB plus DC equals to Y plus Z plus T plus M. Likewise, what is the value of AD plus BC? Again, AD plus BC. AD equals to Y plus T and BC equals to Z plus M. So in total, AD plus BC equals to Y plus T plus Z plus M. Here we can change the orders of the letters, the variables, according to the algebraic identity that A plus B equals to B plus A. So instead of Y plus T plus Z plus M, we can write down Y plus Z plus T plus M. We just change the orders of the letters. So AD plus BC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y plus Z plus T plus M. So those two expressions in the green color, they are both equal to the same third expression, and therefore they are equal to each other. That is to say, AB plus DC equals to AD plus BC. AB is X plus DC. DC is 7 over X. So AB plus DC is x plus 7 over x. AD equals to A according to our definition, and BC equals to B according to our definition. So in total, according to equation 1, we actually found out that x plus 7 over x equals to A plus B. Okay, so in the next step, we did a construction, that is to say from point B, we do perpendicular on DC. Again, from point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC, this point as point S. By doing this construction, we created a quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in size. Why? Because of the simple fact that 270 degrees, that is the sum of those 3 angles, plus 90 degrees, it is equal to 360 degrees, that is the sum of the angles in any quadrilateral. So inside quadrilateral ABSD, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So relate to this quadrilateral ABSD is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB is x, therefore DS must be also equal to x. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A, therefore BS must be also equal to A. So by doing this construction, we created here the right green triangle, triangle BSD. According to our definition, the hypotenuse BC equals to B. And we just right now found out that side BS equals to A. So what is the length of side SC of the green triangle? From the drawing it is very easy to see that SC in total equals to DC minus DS. Again, SC equals to DC minus DS. DC is 7 over x, DS is x. So in total SC equals to 7 over x minus x. So here SC equals to 7 over x minus x. In the next step I copied this right green triangle BSC in a new page and implemented the Pythagoras theorem on this green right triangle, triangle BSC. This is the green right triangle, triangle BSC that I copied from the original drawing. Here by PT is a prevention for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BS square plus SC square. Again, according to equation 2, BC square equals to BS square plus SC square. BC is B, therefore BC square is B square, and it must be equal to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. So this is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to A plus B. Here we use the algebraic identity that states that A minus B square equals to A plus B square minus 4 times AB. According to this algebraic identity, 7 over x minus x squared, if we just substitute 7 over x by A and x by B, we get that 7 over x minus x squared according to this algebraic identity will be equal to 7 over x plus x squared minus 4 times 7 over x times x. So here we have x in the numerator and x in the denominator, so x will get cancelled. So in total, actually, according to equation 2, we found out that b squared equals to a squared plus 7 over x plus x squared minus 4 times minus 7 is minus 28. Okay, so here we have, according to equation 1, 7 over x plus x equals to a plus b, therefore 7 over x plus x squared will be equal to a plus b squared. So in total, according to this equation, equation 2, we actually found out that b squared equals to a squared plus a plus b squared minus 28. Here we open the brackets on this side of this equation, equation 2, and finally found out that according to equation 2, b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab, and we have in the equation also minus 28. Here we have b squared on both sides of the equation, so b squared gets cancelled. So in this side of the equation we left with nothing, that is to say 0, and it is equal. In the other side of the equation we have a squared plus a squared, that is 2a squared, and we have here also plus 2ab minus 28. Here we added 28 to this equation, equation 2, and finally found out that according to equation 2, 0 plus 28 is 28, equals to 2a squared plus 2ab. Here we divided this equation, equation 2 by 2, and finally found out that 28 over 2 is 14, equals to 2a squared over 2 is a squared plus 2ab over 2 is ab. So in total, according to equation 2, we found out that 14 equals to a squared plus b squared. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So what is the area of trapezoid ABCD? The area of this trapezoid ABCD equals to the sum of its two bases, that is AB plus DC, times the height, that is AD over 2. Repeat again, the area of trapezoid ABCD equals to the sum of its two bases, that are AB plus DC, times the height, that is AD over 2. We already mentioned that the two bases must be parallel to each other. That is to say, side AB must be parallel to the opposite side DC. Why AB is parallel to DC? Because of the fact that ABSD is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. Therefore, in rectangle ABSD, side AB is parallel to the opposite side SD. But SD is part of the straight line SC, and is parallel to AB. So if part of the straight line is parallel to another straight line, then the straight line SDC itself must be also parallel to AB. In conclusion, we found out that DC is parallel to AB. Therefore, the two parallel sides in trapezoid ABCD are AB and DC. And therefore, the two bases of trapezoid ABCD are AB and DC. So the area of the trapezoid ABCD equals to the sum of its two bases, that are AB plus DC. The sum of the two bases, that is AB plus DC, times the height, that is AD. Why the height is AD? Because of the fact that the height AD gets 90 degrees with the two bases. Here, this angle equals to 90 degrees, that is to say, side AD gets 90 degrees with the base AB, and here side AD also creates 90 degrees with the other base DC. Therefore, AD is the height to the base. So the height to the base is AD over 2. So in conclusion, we actually found out that the area of trapezoid ABCD equals to AB plus DC, that is the sum of the two bases, times the height, that is AD over 2. AB is x, DC is x plus 7 over x, AD is A divided by 2. But here we have x plus 7 over x, according to equation 1, x plus 7 over x equals to a plus b. Therefore we can substitute x plus 7 over x by ab. We did it. So x plus 7 over x is a plus b, times a over 2. We open the brackets here. A plus b times a is a squared plus ab. So in total this expression equals to a squared plus ab over 2. But according to equation 2, a squared plus ab equals to 14. Therefore we can substitute a squared plus ab by 14 in this expression. We did it. So a squared plus ab is 14. So in total this expression equals to 14 over 2, that is 7. So in conclusion we found out that the area of this trapezoid ABCD equals to 7 square units. We finish with the first question. In the next step, I actually presented to you the second question. In the second question, our mission is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. In addition, we know that side CB of this rectangle is 7 units, equals to 7 units in its length. Inside this rectangle ABCD, side CP equals to 4 units in its length, side PQ equals to 2 units in its length, side QA equals, or line segment QA equals to 5 units in its length. This is angle CPQ, that is a right angle, and this is angle PQ8, that is also a right angle. I repeat again that our mission is to find out the area of this green shape. Okay, so first of all, we join point C and D together by a straight line. And we define the intersection point of diagonal CA with line segment PQ, this point is M. So, by doing this construction, we get that here two vertex angles, and you know that vertex angles are equal to each other. Angle CMP is one vertex angles, and it must be equal to the other vertex angles, that is actually angle AMQ. So those two angles, they are equal to each other according to the rule that vertex angles are equal to each other. So if we define this angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Then we focus on this right triangle AQM. On this right triangle AQM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, according to the same rule, we have here the right green small triangle CPM. This right small triangle CPM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. This gives us the question that PQ in total, PQ equals to 2. So if we define this line segment PM as x, then MQ must be equal to PQ minus PM. PQ is 2, PM is x, therefore in total MQ equals to 2 minus x. In the next step, we actually proved that those two right triangles are similar to each other. That is to say, we proved that the right green small triangle PCM is similar to the right white triangle, triangle AMQ. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually found out that all the three angles of the right white triangle MQA are correspondingly equal to all the three angles of this right small green triangle PCM. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side PM, the right triangle PCM, over side MQ, the right triangle AQM, equals to side PC over side AQ. And again, we derive that PM over MQ equals to PC over AQ. PM is x, MQ is 2 minus x, PC is 4, AQ is 5. So in conclusion, we found out that x over 2 minus x equals to 4 over 5. Here we cross multiply this equation, and we found out that 5x equals to 4 minus 2x. Here we open the brackets on this side of the equation, and found out that 5x equals to 4 times 2, that is 8. 4 minus x is minus 4x. So in total, we found out that 5x equals to 8 minus 4x. Here we added 4x to this equation, and finally found out that 8 equals to 5x plus 4x is 9x. So 8 equals to 9x. We divide this equation by 9, and finally found out that x equals to 8 over 9. So actually, this is line segment PM that is equal to x is equal to 8 over 9. And therefore, line segment MQ that is equals to 2 minus x is equals to 2 minus 8 over 9. 2 minus 8 over 9 equals to 1 and 1/9. 1 and 1/9, it is actually 10/9. So so MQ equals to 10 over 9 and PM equals to 8 over 9. In the next step, I copy this line AQPC in a new page and we analyze this line AQPC. This is line AQPC that I copied from the original drawing. It is given as the question that line segment AQ equals to 5 units in its length, line segment PC equals to 2 units in its length, and line segment PC equals to 4 units in its length. This is angle PQA that is a right angle, and this is angle CPQ that is also a right angle according to what is given as the question. In the next step, we extended side AQ by side line. When you extend a side line by side line, the result is a side line. Therefore, this is a straight line. So if you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle that is equal to 90 degrees, plus the missing angle in total must be equal to 180 degrees according to rule 3 that I mentioned 1 second ago. So this missing angle must be equal to 90 degrees in its size. Okay. In the next step, we did the construction, that is to say, from point C, we do perpendicular on the extended AQ. Again, from point C, we do perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and the extended AQ, this point as N. By doing this construction, we created the right triangle ACN. So we can implement the Pythagoras theorem on this right triangle ACN. According to the Pythagoras theorem in the right triangle ACN, AC squared equals to CN squared plus NA squared. Again, in the right triangle ACN, according to the Pythagoras theorem, AC squared equals to CN squared plus AN squared. So AC squared, that is the square of the hypotenuse, equals to CN squared. CN is 2, therefore CN squared is 2 squared, that is 4, plus AN squared. AN in total equals to 5 plus 4, that is 9. Therefore AN squared is 9 squared, that is 81. So in total, if you found out that AC squared equals to 4 plus 81, plus 4 plus 81 is 85. So in conclusion, if you found out that AC squared, that is the square of the hypotenuse of the right triangle ACN, equals to 85. It is given us the question that ABCD is a rectangle, and you know that all the 4 angles inside any rectangle are right angles. Therefore, this angle ABC, is a right angle. It is 1 out of 4 angles of this rectangle ABCD. Therefore, it is equal to 90 degrees in size. So in the next step, I copied this right big triangle ABC in a new page, and we implemented the Pythagoras theorem on this big right triangle ABC. So actually, this is the big right triangle ABC that I copied from the original drawing. It is given us the question that side BC equals to 7 units in itself, and we just found out that AC squared equals to 85. So according to the Pythagoras theorem, in this right triangle ABC, AC squared equals to AB squared plus BC squared. AC squared is 85, and it's equal to AB squared. AB is the missing side, so we leave it as it is, plus BC squared. BC is 7, therefore BC squared is 7 squared, that is 89. So in conclusion, we found out that 85 equals to AB squared plus 49. Here we subtract the 49 from this equation, and finally found out that AB squared equals to 85 plus 49, that is 36. So AB squared equals to 36. We took a root out of this equation, and finally found out that AB equals to the square root of 36, that is 6. So this side AB equals to 6 units inside, and right here that this is side AB, that is equal to 6 units in its length. So what is the area of the green shape? From the drawings it's very easy to see that the area of this green shape will be equal to the area of the big right triangle ABC, but the area of the big right triangle ABC consists of also the right triangle AQM, and our mission is to find out the area of the green shape. Therefore, we have to subtract from the area of the big right triangle ABC the area of the white triangle AQM, and we have to add to the area of triangle ABC the area of this green small triangle CPM, because of the fact that the area of triangle ABC not include the area of this small white green triangle CPM. So in conclusion, we found that the area of the green shape equals to the area of the big right triangle ABC minus the area of the white right triangle MQA plus the area of the right green small triangle PCM. I repeat again, the area of the green shape in total equals to the area of the big right triangle ABC minus the area of the white right triangle AQM plus the area of the small green right triangle PCM. The area of the height B triangle ABC equals to the base of the triangle that is AB times the height to the base that is BC over 2 minus the area of triangle AQM. The area of this white triangle AQM equals to the base of the triangle that is AQ times the height to the base that is QM over 2. Repeat again, the area of triangle AQ, the white triangle AQM equals to the base that is AQ times the height to the base that is QM over 2 plus the area of this right small green triangle PCM. The area of the small green right triangle PCM equals to the base that is PC times the height to the base that is PM over 2. Repeat again, the area of the green small right triangle PCM equals to the base that is PC times the height to the base that is PM over 2. So the area of triangle ABC equals to AB that is 6 times BC that is 7 over 2. So in total the area of triangle ABC equals to 6 times 7 over 2 minus the area of triangle AQM is equals to AQ is 5, QM is 10 over 9 divided by 2. So in total the area of the white green triangle AQM equals to 5 times 10 over 2 times 9 plus the area of the small green right triangle PCM is equals to PC is 4, PM is 8 over 9 divided by 2. So in total the area of the small green right triangle PCM equals to 4 times 9, 4 times 8 over 2 times 9. So the area of the green shape in total equals to 6 times 7 is 42 and 42 is 21. And here we have 10 over 2 is 5 and 5 times 5 is 25. So in total this expression equals to 25 over 9 plus this expression. Here 8 over 2 is 4 and 4 times 4 is 16. So in total this expression equals to 16 plus 16 over 9. So the area of the green shape equals to 21 minus 25 plus 16 over 9. So the area of the green shape equals to 21 and minus 25 plus 16 is minus 9. So in total this expression equals to minus 9 over 9. So the area of the green shape equals to 21 minus 9 over 9. 81 and 9 minus 9 over 9 is minus 1. So in total the area of the green shape equals to 21 minus 1, that is 20. So in conclusion, we actually found out that the area of this green shape equals to 20 square units. Okay, thank you very much.